We are Meat the Pressure, and this is our study on the compression behavior of artificial meats. We use physics-informed cans to analyze fast and slow loading compression data from plant-based and real meats in order to understand how loading rate affects mechanical properties of meat to improve texture replication. We are assuming a continuum mechanics framework and finite deformation kinematics approach. The meats are assumed to be hyperelastic, isotropic, and incompressible. As for our model architecture, we only use the I1 and I2 invariants since we assumed isotropy. The polynomial terms and exponential terms allow us to capture a wide range of material behavior. Thanks to these 8 terms, we can get up to 255 unique models. This is the Piola stress tensor equation derived from our architecture with a Lagrange multiplier for incompressibility.
We use existing data sets for slow compression at 0.2% per second and fast compression at 30% per second based on sample height, intending to extract stress and stretch for our model. We tested across 5 artificial meats and 3 real meats. To process the double compression test from June's paper, we extracted the first peak above machine noise for all 13 samples. Next, we converted to stretch stress using the dimensions of the meat. And then finally, we interpolated to 21 uniform stretch points to generate curves for each individual meat.
To assess the impact of loading rate on compressive stiffness, we performed a linear regression analysis on both the slow and fast loading data for each meat type. We corroborated each of our calculated compressive stiffness with a corresponding value from previous studies. Generally, we can see that the compressive stiffness calculated using the fast loading data is significantly higher than that of the slow loading data. Next, we trained 2 invariant cans for slow loading and fast loading compression for each meat type and investigated the effect of L1 regularization for each model's performance. As expected, we generally see a decrease in the number of terms as the regularization penalty increases.
We trained models separately on slow and fast data, then tested them on slow, fast, and combined data sets. The R-squared train shows prediction performance on the associated training data, while R-squared test reflects prediction on combined data. As expected, models performed best on their trained data type, but performance varied on combined. We found firm tofu aligned with Blatt's Co. and extra firm tofu with Neo-Hookian for slow trained predictions on combined data. Overall, the slow-trained models predicted worse than the fast-trained models, which generally performed well, with most having an R-squared value of above 0.95. Our hypothesis for this reason is that the stretch interval for the slow-loading data is much smaller, from about 0.9 to 1.0 stretch, while the fast-loading data had a stretch range of 0.5 to 0.9.
So in addition to instrument noise in the fast compression data, our study's greatest limitation is exactly that the fast and slow compression data for each meat was not taken over the same stretch interval, which ultimately led to difficulties for each model to extrapolate beyond the stretch interval it was trained on. Thank you.